Welcome to another lecture of this course, Mathematics for Economics Part 1. So, this particular topic that we have been covering since last two lectures, it relates to continuity, differentiability, the idea of limits, and we have talked about different properties of differentiability, right. When a function is differentiable at a particular point, when is it continuous, those things we have dealt with. We have also dealt with the idea of series and sequences. Not only that, we have also talked about the applications of these series and sequences, for example, evaluation of different investment projects. So, if you have multiple projects to consider, and which one shall you pick up? Suppose you have to pick up only one, or let us say two out of many investment projects that you can take up. Then what is the criterion, or what could be the criteria that help you to pick up a particular project, investment project. So, those things we have talked about as applications of the things that we have been discussing. Now, today what we shall deal with is the last lecture of this particular topic. We are going to talk about another quite important tool as far as mathematical economics is concerned, and this is exponential functions and logarithmic functions. As we shall see later on, that these kinds of function are extremely useful in many analyses of economics. For example, if you want to study the growth rate of income or population, then logarithmic functions, exponential functions, or if you want to find out the present value, right, present discounted value, and in the same thread, if you want to find out the evaluation of investment projects, then you have to find out the present value, obviously, as we have seen. Then also these ideas are very important, the ideas of exponential function and logarithmic functions. So, without wasting time, let us start with our lecture. So, this is where we shall start today's lecture from. So, what are exponential functions? Exponential functions have the general form y is equal to a to the power x. Now, here obviously it is a function. So, y is the dependent variable and x is the independent variable. What is this small a? Small a is any fixed number, right. It could be a constant, but it is not a variable. So, it is given. As you can see, the independent variable is appearing here as an exponent, that is, it is a power on this given constant. So, it is a to the power x. And where do you find such functions? They are often used in economics and finance to deal with economic growth, compound interest rate, discounted of future profits, etc. So, this is the form f x is equal to a to the power x. The exponential function with base a is denoted by f x is equal to a to the power x. So, a is called the base. Okay. This is the base of the function. What is the interpretation of this base? The interpretation of base is, as x changes by 1 unit, the value of the function, that is f x, changes by this factor small a, right. And that you can see, suppose you take f of 0, f of 0 will be a to the power 0, which is 1. Now, you take f of 1, that is, x is changing by 1 unit. So, it will be a to the power 1, which is a. So, you can see that from 1 we are going to small a, therefore, the value of the function is getting multiplied by this quantity small a. So, that is the interpretation of this small a, the base. It is the amount by which the value of the function gets multiplied when x changes by a single unit, 1 unit. Now, if a function is given, then we may want to find out what is the derivative of this function. So, that is the second thing that we are going to look at. The function we have defined a to the power x, but what is f dash of x? So, here is the Newton quotient. Newton quotient is given by this. Sorry for this change corrections that I have done here. So, Newton quotient is given by f of x plus h minus f of x divided by small h. H is the change that is taking place, the increment that is taking place in x. So, we divide the change in the value of the function divided by that h. Now, in this case, since f x is equal to a to the power x, so it will be a to the power x plus h minus a to the power x divided by h, and then the next step we take a to the power x common, and so then we have this term a to the power h minus 1 divided by h. Now, as h goes to 0, we know that we get the derivative, right, that is the definition of derivative. So, therefore, f dash of x is given by a to the power x multiplied by a to the power h minus 1 divided by h as h goes to 0. So, as h goes to 0. Now, at x is equal to 0, so I just substitute a 0 in case of x. Therefore, on the left hand side I will get f dash of 0, and on the right hand side I will get a to the power 0, which is 1 multiplied by a to the power h minus 1 divided by h, right. So, this is the expression for f dash of 0, right. So, therefore, I find that f dash of x, which is this, is equal to a to the power x multiplied by a to the power h minus 1 divided by h, which in fact is equal to f dash of 0. So, I substitute that here. So, I get this expression f dash of x is equal to a to the power x multiplied by f dash of 0. Now, this is very important, this particular relation, and what it means is that the derivative of the function for all values of x exists if f dash of 0 exists, because f dash of 0 is appearing on the right hand side. As long as f dash of 0 is there, so f dash of x exists. Furthermore, I can see that if I divide both sides by a to the power x, then I will get f dash of 0 is equal to f dash of x divided by f x. The proportional change is invariant with respect to x, and this is an important quantity, right. So, f dash of 0 is equal to f dash of x divided by x, and what is the right hand side? F dash of x divided by f x. F dash of x divided by f x is the proportional change, right, and that always remains the same for this kind of function, the exponential, general exponential function. It is not only always same, and it is given by this quantity, it is given by f dash of 0. Okay. And what is f dash of 0? I said that this is an important quantity, but what is the interpretation of f dash of 0? Well, here I have drawn the function. So, you have x along the horizontal axis and y along the vertical axis, and this function is going to look like this. It is an upward rising function, and it is going to intersect the y axis at a at a positive intercept, and that point where the intersection is taking place, at that point I have f dashed of 0, right, the slope. This is the slope of f x, right, at x is equal to 0, and this is given by f dashed of 0. And therefore, basically if I draw a tangent to that graph at this particular point of intersection, then the slope of that tangent is f dashed of 0, right. You might ask, why do I draw this function like this? It is an upward rising function, because as x goes on rising, obviously a to the power x will go on rising, and we also know that as x goes on rising, y will go on rising at an increasing rate. That we shall let us consider that for future discussion. It will come just shortly after this, that as x goes on rising, y rises, but it rises at an increasing rate. Therefore, you have function which is rising at an increasing rate. Now, we know that f dashed of 0 is equal to, this is h, is equal to a to the power h minus 1 divided by h, and this is a function of a. So, as a changes, this thing will also change, right. F dashed of 0 is this. So, f dashed of 0, as we know, it is the slope of this function at this particular point. So, for example, suppose small a is equal to 2, then one can calculate that f dashed of 0 is equal to not exactly equal to, but approximately equal to 0.7. That is the slope of this line. This line, if you take small a is equal to 2, is equal to 0.7, which is close to 0.7. And if you take a higher value of small a, suppose small a is equal to 3, then f dashed of 0 actually rises, and it is approximately equal to 1.1, right. That is what is meant by this, that as small a rises, the slope of this function at x is equal to 0 rises. So, basically this tangent is getting steeper and steeper. Now, invoking the intermediate value theorem, at some value of a between 2 and 3, f dashed of 0 will be equal to 1. And I have talked about intermediate value theorem. F dashed of x or f dashed of 0 is a continuous function of a, right. As a goes on rising, we have seen that this f dashed of 0 goes on rising. So, at some point between 2 and 3, it must be the case that f dashed of 0 will be equal to 1, because at 2 f dashed of 0 is equal to 0.7, and at 3 it is very close to 1.1. So, therefore, there will be some value between 2 and 3, maybe very close to 3 rather than 2. At that point, f dashed of 0 will be equal to 1. And this particular value of a is important. It is an irrational number, and it has been given the name E, and the exact quantity of t cannot be specified because it is an irrational number. So, but it is very close to 2.71828, and it goes on like that. So, the main thing that we are getting here is that I have defined a quantity which is small e, and this is very close to 2.71818, and what this E does is that at this particular value of E, if I take a is equal to this particular value, then f dashed of 0 is equal to 1. Okay, the slope becomes equal to 1. Now, this is known to us, f dashed of x is equal to a to the power x multiplied by f dashed of 0, and for a is equal to e and for a is equal to e, we have just seen that f dash of 0 is equal to 1. Therefore, if I put f x is equal to e x, then f dash of x is equal to e x. So, because this part is becoming 1 and this part is becoming e to the power x. So, therefore, f dash of x is equal to e to the power x. Now, this function is very often encountered in economics. This is called the natural exponential function, this function f x is equal to e to the power x. For the natural exponential function, the slope at x is equal to 0 is 1, right, that we have just seen. That is how it is defined actually. The expressions half of e to the power x minus e to the power minus x and half of e to the power x plus e to the power minus x occur often, and these have been given some special symbols. These symbols are given as this: sin h x, this is called hyperbolic sine function, and this is equal to half of e to the power x minus e to the power minus x, and cos hyperbolic x, which is equal to half of e to the power x plus e to the power minus x. This is the cosine function. So, this sine and cosine functions are actually functions of natural exponential functions. Now, relatedly, there is this logarithmic function. So, what is the idea of a logarithmic function? Suppose f x is equal to a to the power t. Okay. I should write this as f of t because it is a function of time, suppose t is time, and we want to find the time it takes for the value of the function to double or treble, etc., right. So, time is changing. So, therefore, this right hand side will go on changing, it is going to go up, and if that is true, then at what time the value of the function will double or it will treble or it will rise by 100 times, etc., etc. Now, notice however that this will rise if you have a to be greater than 1. Okay. Now, here is an example. Suppose I have 1000 rupees in the bank which pays me 5% rate of interest annually. Now, how long will it take for the money to grow to 10,000 rupees? So, the money is going to go up by 10 times and the rate of interest in the bank is 5%. I wanted to find out what is the time it will take. Now, basically to find that out, I have to solve this equation. It is 1000 multiplied by 1 plus 0.05 to the power capital T is equal to 10,000. So, I have to solve for capital T. Now, this boils down to this simpler expression 1.05 to the power capital T is equal to 10. In general, the solution to such problems involves solving an equation of the form a to the power x is equal to b. Right here, a in this particular case, a is equal to 1.05 and b is equal to 10. And we take the natural exponential base, which is we know is small e, that was our natural exponential base. So, instead of small a, I am replacing the small a by small e. So, I get e to the power x is equal to b. Here in e to the power x is equal to b, the unknown occurs as the exponent. So, x is the unknown, right. E we know and b is also known to us. What is not known is that small x, and that is appearing as the exponent. So, it is the power, So, here for example, the t has to be found out. So, but t is appearing as the exponent. We call x here as the natural logarithm of b, right, and we write this as x is equal to ln b, log natural b. So, x is equal to log natural b, and if I substitute back that in this expression, what I get is e to the power ln b is equal to b. So, in other words, e to the power ln b is equal to b, this is true for any positive number b. So, that is important, b has to be a positive number. Now, here are certain rules for natural log or ln. If x and y are positive, then log of x y is equal to log x plus log y, log of x divided by y is equal to log x minus log y, log of x to the power p is equal to p multiplied by log x, log of 1 is equal to 0, log of e is equal to 1, and x is equal to e to the power log of x that we have just seen, and log of e to the power x is equal to x. However, we can see that log of x plus y or log of x minus y, they do not have any easy rules, like for example, log of x multiplied by y. So, it is not the case that log of x plus y is equal to log x plus log y. Okay, here are some examples to practice. Now, suppose we have to solve for x for these two problems, and the first problem is this: e 7 multiplied by e to the power minus 2x is equal to 16. Okay. So, from this I divide both sides by 7, I get e to the power minus 2x is equal to 16 divided by 7, and then I take natural logarithm of both sides. Okay. Now, if I take log of e to the power minus 2x, then it simply becomes minus 2x. Okay. So, how do I know that? Here, this is the rule that I am using here: log of e to the power x is equal to x. So, log of e to the power minus 2x is equal to minus 2x, and on the right hand side the expression remains the same. So, therefore, x is equal to minus 1 divided by 2 multiplied by log of 16 divided by 7, and this turns out to be half of log of 7 divided by 16. So, I just have the reciprocal of 16 divided by 7, which is here, and it becomes 7 divided by 16. And why this is so? Because I have here used this rule, the quotient rule. Okay. Now, the second one, let us look at that: b, capital B, multiplied by theta e to the power minus alpha x is equal to small p. So, we have to solve for x. So, I take these constants b theta to the right hand side, and then I take the log, natural log of this e, log of e to the power minus alpha x is equal to log of p divided by b theta, and this will simply become minus alpha x, right, because log of e is equal to 1, and on the right hand side I have log of p divided by b theta, and so I get x is equal to 1 divided by alpha minus of that multiplied by log of p divided by b theta, and again I use the rule for quotients, and I get 1 divided by alpha log of b theta divided by p. Okay, so this is how we solve for x. Now we define a function. One can define a function as x is equal to g of y is equal to log of y. So x is a function of y. If y is a function of x like this, y is equal to fx is equal to e to the power x, and this is illustrated here. The graph of y, right, here y is equal to e to the power x, the exponential natural exponential function. It intersects the y axis at 1, that we have seen before. Why? Because if you put e to the power 0, it becomes 1. For each positive value of y, one can read the corresponding value of x. Okay. From the graph, the function x is equal to gy is defined for all positive value of x, and it is the inverse of y is equal to fx. So here x is equal to log natural of y if y is equal to e to the power x. So one is the inverse of the other. So this is what we have done here, right. I have turned this figure around, right. Now along the vertical axis I have the log. So this is log. So instead of writing it log of y, I am writing is log of x, because x is generally taken in the horizontal axis. So here y is log of x, right, that is what we are getting here. And here are some basic properties of log function. If you take log of 1 divided by e, you will get minus 1, because log of 1 divided by e is equal to log of e to the power minus 1, and that becomes minus 1. Log of e is equal to 1 and log of 1 is equal to 0. So basically this point is 1, and if you have some point here which is 1, then this should be e. Now what about the derivative? If you have x is equal to e to the power gx, where gx is equal to log of x, then we get, I am taking the derivative of this function. So with respect to x, I will get 1 is equal to g prime of x multiplied by e to the power gx. I am just using the formula for the derivative of an exponential function, and therefore I will get g prime of x is equal to 1 divided by e to the power gx. But what is e to the power gx? E to the power gx is x. So g prime of x is equal to 1 divided by x, and that is what we wanted to find out. So g prime of x is equal to 1 divided by x, and this is nothing but ddx of log of x. So that is the formula for derivative. So derivative of log of x, that is natural log of x, is equal to 1 divided by x. Now 1 divided by x is a positive number, because x is always positive. Since this is positive, it implies the first derivative of natural logarithmic function is always positive. But if you take the derivative of this, then you will get the second derivative, then it becomes a negative quantity, minus of 1 divided by x square. So the second derivative is negative of a logarithmic function. Now if you have a composite function, so what happens if you have a composite function like y is equal to log of u, where u itself is a function of x, u is equal to fx. Then how do I find the y dashed, that is the derivative of y with respect to x? I use this formula, and I will get f dashed of x divided by fx. This is the proportional change in u with respect to x, and that is equal to y dashed. Logarithmic differentiation, there is something called logarithmic differentiation. I start with an example. Suppose y is equal to x to the power r multiplied by bx minus c to the power p. I have to find out y dashed. So, what I do is that I take the natural logarithmic of both sides of this particular function, and if I do that, I will get log y is equal to r log x plus p of log bx minus c. Now, I take the implicit differentiation of both sides with respect to x, right. So, what I will get is y dashed by y, okay, y dashed by y is equal to r divided by x, yes, r multiplied by 1 divided by x, plus p multiplied by 1 divided by bx minus c multiplied by b. So, that is what we are getting here. Okay. And from this I get y dashed, because I have to find out y dashed at the end of the day. So, y dashed will be y multiplied by this expression on the right hand side. So, it gets equal to y multiplied by r divided by x plus p multiplied by b divided by bx minus c, and then I expand the y, this is the y. So, I get this expression as my y dashed. Now, I come to the idea of elasticities. Remember, I introduced the idea of elasticity. Now, we shall see that with logarithmic function, the elasticity is somewhat easy to find. Elasticity of y with respect to x is given by, as we know, it is given by x multiplied by y dash divided by y. Now, suppose I have to find out what is the elasticity of y is equal to e to the power x or y is equal to log x. These two functions are given, I have to find the elasticity of y with respect to x. Now, from y is equal to e to the power x, if I take the log of both sides, I will get log of y is equal to x, and then I differentiate both sides with respect to x. So, through implicit differentiation, I will get y dashed by y is equal to 1, and so I know the formula of elasticity is E y x is equal to x multiplied by y dashed by y, and y dashed by y is equal to 1. So, this becomes simply x. So, elasticity is equal to x for this first function. For the second function y is equal to log x, what I do is that I take the derivative of both sides with respect to x, then it becomes y dashed is equal to 1 divided by x, because I am taking the derivative of log x. And what I know about the elasticity, I use the formula. I have already found out y dashed, I substitute that here, right. This is 1 divided by x and multiplied by 1 divided by log x because y is there, and this becomes equal to 1 divided by log x. Now, all these were logarithmic functions with base e, right, natural exponential. Now, if I take log with other bases, then also it can be defined. For any given fixed positive number small a, if I have a to the power x is equal to b, we call x to be the logarithmic of b to base a. Okay. So, write as x is equal to log of b base a, and therefore, I can substitute this back here. So, a to the power log of x base a is equal to x. So, here are some examples. Suppose you have log of 1000 base 10, then you can express 1000 as 10 to the power 3, and this will become simply equal to 3, right, because 3 will come in front and log 10 base 10 is equal to 1. From a to the power log x base a is equal to x, taking natural log of both sides, I will be able to get this log x base a is equal to natural log of x divided by natural log of a. Now, natural log of a is a constant. Thus, log of any number with base a is proportional to the natural log of the same number, because this is equal to log of x multiplied by 1 divided by log natural of a. So, it is proportional to log natural of x. And rules for log natural are applicable for log in general as well, that is the product rule, quotient rule, etc. are applicable. Now, characterization, I come to characterization of small e, because we have found out this small e, but this can be characterized in a different manner also apart from what we have done before. Now, it can be shown that if you take the limit of log natural 1 plus h to the power 1 divided by h and limit h goes to 0, then this goes to 1, this becomes equal to 1, which means that forget about the log natural, this particular quantity, this will go to e, that is why log of this thing goes to 1. Or limit of this, so instead of h I am taking the reciprocal of that, suppose that is n. So, I am replacing h by 1 divided by n, and if h goes to 0, then n goes to infinity. So, this thing should be correct, that limit n goes to infinity 1 plus 1 divided by n to the power n will be equal to small e. So, this is another way to understand the small e. Taylor's formula can also show for, using Taylor's formula we can also show for some c between small x and 0, e to the power x is given by this 1 plus x divided by factorial 1 plus x squared divided by factorial 2 plus dot 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 plus x to the power n divided by factorial n plus, this was the correction term or the error term, this is x to the power n plus 1 divided by n plus 1 factorial. So, E x can be found out through this Taylor's formula as well. Now, I come to applications, maybe I shall not be able to cover all the applications in this lecture itself. So, some parts will be left out to be covered in the next lecture. Applications, suppose there is a function like this, f of t is equal to a e to the power small r multiplied by t. So, here capital A is constant, r is constant, e we know, right, it is that natural exponent, and t is the variable here, t is the time. For this kind of functions, if I take the derivative of both sides with respect to small t, I get f dash of t is equal to r f of t, and this is correct for all values of t. In other words, for such functions the proportional rate of change, that is f dash of t divided by f t, is equal to r, and r is a constant as we know. So, it is a fixed quantity, that is for these functions the proportional rate of change is given, it is constant. And the opposite is also correct, in fact, that if the proportional rate of change of a variable is constant, then the form of the function is like this particular form. Now, suppose f t denotes the population of a country at a particular time t, right. F t, as we have seen, it is a general function. So, I can interpret f t in any way we like. So, let us suppose f t is the population at a particular point t of a particular country. Now, what is f dash of t divided by f t? We can call this as per capita growth of population or per capita rate of change of population, right. I am taking the f dashed, right, which is the change per unit of time, and I am dividing that by the original population. So, that will give me the per capita growth rate of population. Now, f dashed of t divided by f t is equal to r. Suppose that is the formula that is applicable for a particular country, that per capita growth rate of population is constant, it is given by r. But if that is correct, it implies a very simplistic model of population growth, where the population rises exponentially all the time, because behind this we know there is this function f t is equal to a e to the power r t, but this is an exponential function where r is constant. So, it basically means that the population is rising all the time at an exponential rate of growth, and that may not be correct for a long period of time. It may be correct for a short duration of time, but may not be for longer time durations. It might be more realistic to assume that the population starts to decline above a particular limit, which is the carrying capacity of the environment. So, the idea is that as the population rises to very high levels, it is possible that the environment will not be able to sustain that high amount of population. So, behind this is the old Malthusian idea that population is limited by the natural resources of the country, and with the growth of pollution and environmental hazards and different diseases, we are also seeing the return of that kind of idea to the mainstream, that the environment is very important. Population can just go on rising, but after a point of time it can hit a upper limit, and after that population might decline in fact. And this more realistic but little bit complicated picture is captured by this equation: f dash of t is equal to r of f t, but then there is another factor here, 1 minus f t divided by capital K. Now, as you can see that as f t becomes higher than capital K, then this term becomes negative, and if this term is negative, then f dash t is negative, which means population is going down. So, basically f dash t becomes negative if f t exceeds capital K. Here for f t very small compared to K, the carrying capacity, this is carrying capacity, population rises exponentially. So, this part becomes equal to 1, roughly equal to 1 if f t is very small compared to capital K. So, in this case there is no environmental problem, population has a lot of margin to grow, but as f t approaches capital K, it slows down, right. So, imagine f t not equal to K, but very close to K. So, then this term will be very close to 1, right. In that case 1 minus a term which is very close to 1, then this factor becomes close to 0. So, in that case f dash of t approaches 0. So, that is what is meant by this carrying capacity, the idea of carrying capacity capital K. It sets an upper limit. You do not actually have to reach that. Even if you are very close to that carrying capacity, population starts to slow down. Okay. It can be shown that if I start from this particular form, I can go to this particular form, right. F t is equal to capital K divided by 1 plus a e to the power minus r t. Now, this is called a logistic function, and in this function suppose you take t approaching infinity, right, and if you take t approaching infinity, what we can show that this function, the value of the function f t approaches capital K if capital A is greater than 0, because this term as t goes to infinity, this term goes to 0. So, therefore, f t becomes very close to capital K. So, geometrically how does this look like? Geometrically this is how it looks like. You have time here on the horizontal axis, and on the vertical axis you have the population, which is f t. So, the population starts to rise at a very steep rate first, then it sort of slows down, and you can see that it approaches capital K, but it will not be able to reach capital K ever. As t goes to infinity, it goes on approaching capital K. So, this was an application of logarithmic function, exponential functions in case of population growth, and what does it have to deal with environment. Now, we take up another topic, which is log linear relation, because again this is used often in economics. Suppose y and x are related as follows: y is equal to capital A multiplied by x to the power b. So, here capital A and small b are constants, small x and small y are variables. Now, we take the log of both sides, right. This could be log with any base, I am not specifying the base. So, log of y is equal to log of a plus b of log of x. Now, from this I can see that log of y and log of x, they are related in a linear manner, right. Log of y, you can think of that to be another variable altogether, and log of x is another variable altogether. So, maybe capital Y and capital X, then capital Y and capital X are linearly related to each other. Now, this kind of function is called log linear relationship. It is a linear relationship, but log of the variables have been taken first. Okay, now we take y to be an exponential function of x. So, y is equal to a multiplied by b to the power x. So, it is an exponential function of x. Now, if I take the log like before of both sides, then I get log of y is equal to log of a plus x multiplied by log of b. Here also we are getting kind of linear function here, but in that linear relationship log y can be considered one variable and x is the other variable. So, one of the two variables is a log function, the other is not. Here log of y is a linear function of x with log b as the slope, right. Log b is the slope here. Now, elasticities, as we have seen, are closely related to logarithmic differentiation. So, suppose you have elasticity of y with respect to x, this is given by E y x. Now, we know the formula for that is this: x divided by y multiplied by dy dx. So, I rewrite it like this, and dy by y is nothing but d log y. D log y is differential of log y, and therefore, I get this form, that this becomes d of log of y and divided by d of log of x. The base could be anything, it could be natural logarithm, it could be non-natural logarithm. For a log linear relation, log y is equal to log of a plus b of log x. B therefore is the elasticity, because if you take this and you take the d log of y d log of x, then it becomes small b, and d log of y d log x, we have seen that is the elasticity. So, b is the elasticity. Therefore, in the relation y is equal to x to the power b, b is actually the elasticity of y with respect to x. So, this is an important relationship which is often used in econometrics. I think I will stop here and take up this particular topic in the next lecture, and in the next lecture, if we have time, we are going to start with a new topic as well. So, I will call it a day, and thank you.